But remember that until this tutorial, we're still dealing with stationary charges. Okay? Either tutorial 1, tutorial 3, both are on stationary charges under the topic of electrostatics. So in the tutorial 1, when we learn this electrostatics, for the stationary charges, we mentioned that once you know charges are stationary, if you know the charges, solution always given by this integral. Okay, these equations we described is the result of Coulomb's law, which is the only law in electrostatics, plus principle of superposition. So which means that if you are given any, just illustrate, if you are given any charge distribution, the charge is not moving, first calculate delta Q, it produces a delta E. So that will be this term here. Integrate all the charges means superposition, you get this integral. So there is no exception. Once you know charges, stationary charges, you know the source, you know the field everywhere. The solution also given, which is given by this terms we call direct integration. Direct integrate Coulomb's law. First one, look at delta Q. Where are your charges? If the charge is a point charge, concentrate at one point, integrate of delta Q will be Q. You will directly obtain Coulomb's law for point charges. If it is distributed along the wire, just illustrate it, you just put a small length, cut it into a very small length. Delta Q, at this point here, the charges basically rho L here. You treat it as if it is a point charge, apply Coulomb's law, work out the field here, and integrate all the charges. So you have delta Q, it is along the wire, rho L dl, distributed on surface, rho S dS, and so on. Okay? Next one, we need to know how far it is. Remember Coulomb's law. Even without calculating, you should know directly proportional to charge, inversely proportional to R squared. Which means that you need to know how far delta Q to the field point. Okay, so that's why we calculate the vector R, which is important. Today we also calculate the vector R. Vector R gives you two information. One is how far away, and next one the directions of E field. For electrostatic, if it is positive, it go away. If it is negative, it go into negative charge. That's why this vector R captures both the magnitude and directions of the E field produced by delta Q. Okay, vector R is computed using field point minus source point. Field point is the point you wanted to calculate electric field. Source point is the coordinate of delta Q. Once you obtain the vector R, you substitute it, you can work out the distance, absolute distance of this vector R, sub in here and integrate all charges. In this course, whenever integration are difficult, as you can see in tutorial 1, formula or tedious formula will be given. So, but you need to simplify it. In some cases, you need to simplify so that you can write a given formula, usually apply symmetry. How do you know you can apply symmetry? You look at the field point. Example, at this point here, not possible because it doesn't any it is not located at center or any charge distribution. You move the charge at the center here, cut it into half, then you can apply symmetry along this line. Is that okay? Whether you can apply symmetry or not, you look at whether the field point is at the center of the charge distribution. Okay. So when it is at the center of the charge distribution, you can either use a physical reasoning, draw the diagram, look at center means equal distance. Magnitude will be the same. You need to decide whether the field add up or subtract. Okay? And this solves all problems during electrostatics. So what we ask, then why bother to learn electric potential? Anyone tell me whether we need electric potential? Is it a necessary concept? Hey, you learn the electric potential. We need electric potential. Hey, who haven't signed? Sign already, huh? Anyone tell me whether we really need electric potential? Can we analyze our electrostatic problem using Coulomb's law? without the need to use any electric potential? Yes or no?
Yes.
Okay, why?
Because they are all like related. You get a feeling, you get everything.
Okay. Generally, we can only measure forces. Okay? If you learn the electromagnetic, you know ultimately what we want is the force. F equals, this is called Lorentz force law. Those do this, basically you will encounter this equation here, Q E plus V cross B. Okay? Generally, if you know the electric field, if there is no magnetic field, you know the force, it can interact with any charges. When you interact with the charges, F equal to ma, you know the acceleration, you know the response. Okay? So then, why we wanted to introduce electric potential? Simply because if you look at this integral here, there one complexity here. You are integrate a vector. Okay? So you look at the diagram here, and the delta Q here, the vector are going in this way. Delta Q is here, it's going in different way. This is not a good way to integrate any of these vectors. Very difficult to integrate. You keep track of directions. So you observe in tutorial 1, usually you are given the chart which is highly symmetric. By using the symmetric condition, you can identify X component cancel, only remain Y component, and so on. So that you make this vector R constant vector. Identify from symmetry, you bring the vector out, you integrate a scalar. Right? So as a result, you can simplify the integral by using symmetry. But in general, it can be complicated to integrate. So now, is there any good way to simplify this integral? So you learn electrostatic, you know that from Maxwell equation I mentioned that you have this curl of E, electrostatics. For electrostatic field, curl of E equal to 0 divergence of E equal to rho V. Okay, these are the two equations governing electrostatic field. So, which means that from this integral here, if we take the curl, always 0. As long as the charges are stationary, there is no curl. And if you recall from previous tutorial, this identity here, curl of gradients of F, is always equal to 0. That means that you can write your E equal to gradients of F. A scalar function, if you can find a scalar function F, you know the E. Okay? Instead of solving E field directly, which is a vector, we break it down into two steps. First, compute the function F, and we call it electric potential. Why you put it a minus sign here is to make it consistent with your circuit theory. You found that when you learn the circuit theory, how do you define potential difference? If you have capacitor here, you have plus sign here and minus. We know from electrostatic, we define the E field. Positive go to terminate in negative. Directions of E, higher potential to lower potential. Potential different when you measure. This is the reference, lower potential to higher potential. Always opposite. So this gradient here basically show you that it's a maximum slope. Okay? And in opposite direction. So you found that they are always, this is the same potential, always 90 degrees. If you have a potential here, example. Okay, suppose this is 1 volt, this is 2 volt. Okay? So the E field, once you know the potential, you know the E field how? Because from this point example, higher potential to lower potential. Through the shortest path, 90 degrees, that will be your E. Okay? Before that, if they are close together, higher E. So here also from here, higher potential to lower potential. That will be your E. Okay? So basically, it's a convenient way. If you know electric potential, you know the E field. Okay, so now we left with how to find this electric potential, which is a scalar. In many cases, a simpler topic. Okay, so what is the meaning of this electric potential? Is integrate Try to interpret the result here. You found that electric potential basically is E is Newton per coulomb. Okay, you bring 1 coulomb of charge from far away, infinite example. That will be force experienced by 1 coulomb of charge. Okay, suppose we have 1 coulomb of charge. From very far away, you bring it to point P. So they integrate infinity to P. Okay. Because electrostatic are stationary, are irrotational, the path taken not important. Okay, that's why you only need to define infinite. Usually assume is 0 volt. Every point have a unique potential. This is only possible if you have irrotational field. So you know that irrotational field integration is independent from a path taken. So if you choose 1 coulomb of charge, let's say joules per coulomb. You bring 1 coulomb of charge from far away, assuming that point charge far away is 0 potential. You bring it to the field point P, that will be a force. When the force experienced by the charge dot with dl, what is that? What is F dot dl? Work done. How much energy required to bring 1 coulomb of charge from far away to that point? What is the minus sign here? Electric potential is defined as external work required to bring 1 coulomb of charge to that point against the if it means that you need to supply the work. Okay? If your answer is positive, that's why whatever energy you bring it, you will increase the potential at that point. Okay? If the answer is positive, means that the work done is positive, you need to supply external work to bring it to the field point. If it's negative, means they extract energy from the field. Well, before you do it, just try to explain a little bit of the electric potential, at least you know why you need to do it. And because this is only the energy, the unit is joules every coulomb. If you know the E field, if you know the electric potential, you know that at that point, how much energy is required to bring to that point per coulomb. If it's 10 coulomb times 10, 1 microcoulomb times 1 microcoulomb. Well, it's a scalar, no direction. Okay, so when you do the symmetry, you only worry about positive or negative charge. That's it. Okay? So now, basically it's a meaning. The detail how to write the formula. You refer to the video lecture recording. I just said the result here. The solutions for static field is also very similar. Once you know stationary charges, you know the potential. Okay, because they are related, as we mentioned that electric potential and electric field intensity are related. But you look at this integral here. Directly proportional to the charge again, which means that same thing, superposition principle can be applied. If you know 1 delta Q, the rest you just integrate. Superposition. Directly proportional charge, but inversely proportional to R. That's why if you look at the formula sometimes, the given formula, R is square root. If 2 power half usually suggests that you use electric potential approach. If it's 3 over 2, like tutorial 1, that will be direct integral approach. But for all the problems, you can solve either using the approach in tutorial 1 or tutorial 3, they are identical. Except sometimes one method is easier than the other. It's okay? But in many cases, electric potential is simpler because this guy is a scalar. And when you do the symmetry, remember, only 2 things. Charges, distance. If the charges are the same, distance the same, potential will be the same. Example here. Suppose you have the plane of charge here. Suppose you have the charge here. Okay? Positive charge example. Either you have 1 meter here or 1 meter here. Same. Because charge is the same, distance is the same. 1 meter up or 1 meter down, same potential. Okay? But E field is different. E field is a vector. If you have positive charge, you are up, point away. If it's bottom, point away. Okay? Opposite direction. Okay? So when you apply symmetric condition, only charges and distance. If charge the same, distance the same, mean potential the same. Okay? And give me another example. Suppose you have a circle here. Charge. Okay? Circle on the extra plane. If you have a cycle here, you look at all the charge here. All same. Same charge, same distance. Total charge divided by 4 pi r. Q over 4 pi r. Okay? So that is why we introduce this as engineering approach. Conceptually, you can always do the direct integral, but as a matter of fact, this approach in many cases is simpler. So once you do this integral, next one followed by differentiation. Okay, minus gradients of V basically is a differentiation because the Bell operator for cylindrical and Cartesian formula given in the appendix. Don't need to remember. Remember, that's basically del AX, del over del X plus AY, del over del Y plus AZ. Of course, there are another equivalent one in the cylindrical form. Clear? So now, we summarize the approach for this tutorial. Instead of using this, tutorial 1, use this one to solve question 1 and 2. In this tutorial, we just do the different approach. First, calculate electric potential, followed by differentiation. Those you have time, after you solve this, you go back to solve this one. You can see the difficulty. What is it? Okay? Either approach will work. Clear? Any question before we start? It's simple, very similar. Before that, how to solve this? Same approach. Okay? First one, calculate delta Q. Exactly the same. Either line charge, survey charge, same thing, delta Q. That's why I say that the approach is similar. Next one, calculate vector R. But we don't need to know the direction. We can, once we know the vector R, you can also obtain the distance. The magnitude of R sub in here. Do the integration. So, if your integration formula is given, you same rules apply if your field point is at the center of any charge distribution. Apply symmetry to simplify it. Except, take note that when you apply symmetry, no direction involved. Only absolute distance and charge. And finally, do the after you do the integration, do the differentiation. Bear in mind that integration can be difficult, so formula sometimes will be given whenever integration is tedious. But differentiations, to start expect every student should know how to differentiate. Once you know the function, you should know how to differentiate. For example, differentiation by f1, f2. How do we differentiate? Multiplication of the function, how to differentiate log function, exponential function, all these are expected to know how to do differentiation. Okay? Question? No. Then the red, who haven't signed? I asked few times.
Wait, yeah, we signed. Hey, but I never see Thomas' name. He had brought. I don't know. That's why I asked him. I asked him a good. I can't find him. I think we just checked. He bring. Yeah, he bring.
Wait, Thomas name
No questions.
I cannot find him.
Very simple.
Ryan.
1, 2, 3, solve.
You guys.
First ask yourself where is delta Q, how far away? Come here and say. Yeah. Take your pen, come here and sign.
The difference between the operators.
The dot.
Yeah, the cross dot or this like what?
Cross is the determinant.
Okay.
I don't know what's dot.
I say you, but then the main
This
key
is just to
difference is
take
to
note that when you do
identify
especially
what
OICs,
is used for the rotational.
or
Right?
who is,
What-
I don't know
because
whether it
got
came
a
out or
lot
not.
of-
The thing is, definition, electric potential is the energy
Electric,
required to bring 1 coulomb of charge, this is joules per coulomb, from far away, which is infinite, to point P. The force experienced by the charge, minus sign against the E field, the work required
Yeah,
would
there are a lot
be
of
unit
properties
joules every
like
coulomb.
if
Because
it's
sometimes
like
you
equals
are
to
quiz,
0,
they
then
ask you the
rotational
unit,
or
this is
something like
bonus
that. So I went to screenshot.
Okay, either
They all
joules
got
per
explained a
coulombs.
bit.
And if you want to
Like,
get
the
the
maximum
potential
equation is
difference
derived
between,
by what
if we
only?
move it from point
ChatGPT,
1 to
yeah.
point 2, then of course you can say infinity to 1 minus infinity to 2 minus infinity to 1. Basically, integration is point 1 to 2. Okay? That is what you're going to measure using a voltmeter. For example, you connect your voltmeter between point 1 and 2, you actually integrate the E field along the wire of your along the wire of the voltmeters. Okay? So we don't need to specify how the wire run about because integration path is basically is independent from the path taken from 1 to 2. Okay, that's why in electrostatic you don't care. Okay, when you put your voltmeter, sometimes you just connect any way you like. It doesn't matter. The integration path from 1 to 2 is not important. Okay, but you found that in when you go to time varying field, that will be different. Okay, clear? So take note of the assumption here. This is still under electrostatics.
Also here.
This is just an example, huh? Example, you are given the E
Oh,
field,
no, salah.
electrostatic field, and you are asked to point 1, point 2. I just simply draw a simple example. You can do your. I understand that in your OICs they give you a 3-dimensional 1, 2, 3 to 4, 5, 6, and 4. But the concept is the same. Suppose you move the child along this path here, path C here. This can be complicated path. But in most cases, the easiest way is to move along X, then along Y. Okay? Because when you move along X, your DL will be AX dx, move
Just so
along
we
Y,
think this is a lot of truth
DL
also.
will be AY dy. Refer to reverse tutorial, Stokes theorem, we do this
It's not
y
true.
integrals.
He got say weak one.
Okay? So in most cases, you resolve the path along X, Y, Z.
But just
Easier
need
to
to,
integrate.
you need to score full mark.
Okay, of course, for those who are very ambitious, you want to integrate along this curve path of same. Okay, why it can be done? Because irrotational field equal conservative field. You move the charge here, and come back.
But it's all true.
Will be
You
0.
screenshot then put ChatGPT.
So assuming that you bring along C is 5 volt, 5 joules per coulomb. So if this is 5, this path must be minus 5. You reverse the path, must be 5. Okay, that is the rationale of resolving the path because we knew that by changing the path, it doesn't change the direction. Okay, but it only works if it is irrotational. Okay, how do you define irrotational? Curl of E equals 0. So if found that in general it is not true. If we look at Maxwell equation, curl of E minus del B over del T. So we look at it, what will happen when you have the terms at the other side. Okay, that means that when it is not rotational, then the potential cannot be defined. Okay, some of them may say, can you give an example? I'll give you one example you probably know. Suppose, this is just to let you know that tutorial 5 will cover it. Suppose you have a wire. Everywhere look the same. They say total resistance 2 ohms. This wire. And if you have suppose you have the flux going into space changing with time. This thing is not equal to 0. You will find that EMF will be induced, Faraday law, current flow here. Suppose current is 1 amp. So you have A and B. Anyone can tell me if you put the voltmeters or just as simple A and B, which one higher potential? Which one higher potential? Huh? Which one higher potential? Same. Okay, some say same. Then may I ask, if it's the same potential, why current will flow? Correct or not? The fact that current will flow, it is not the same potential. So then the next one is, which point is higher potential? But you look at it very straight, I cannot say A or B, it looks the same when you rotate it here and there. Huh? Anyone can answer this one? You see, if I put a voltmeter here, what is the reading of voltmeter? Huh? You see, this is 1 ohm, correct? 1 amp, 1, because 2 ohm divide this 1 ohm is 1 ohm, 1 times 1 volt. Correct? But you have to be here. If I fit the wire here, it will be different. Why? Because integration part here is important. Okay, because this is no longer irrotational field. Okay, here to here, this one higher potential, this one lower potential. From here to here, B higher potential. You have to define the path. Okay, that's why things become more complicated. But we don't touch this time varying field or rotational field yet. Yeah. But remember the rotational field. That's why they can generate electricity, rotational field. They rotate the magnet. Okay, they generate, move it back to the same point, it still can generate electricity because of rotational field. Okay? So you go back to the same point doesn't mean zero energy delivered to the system or extract from the system. Okay? So far, that's why it's useful to know the assumption. Because we need to know that all so far what we did, we can resolve the path because of irrotational field. Okay? Okay, now this one is just a simple thing you can do the exercise. Let's look at the tutorial question 1. Okay. 2 parallel circular dish. Circular dish means that it's not wire loops. Charger will distribute it on the dish, means that coulomb per meter square. Delta Q will be rho S ds. Okay? If you have a wire loop, then the charge will be rho L dl. Clear? So, 2 circular dishes usually apply superposition. You can do it one by one. There are 2 separate sources. The simplest way is look at one, solving one, and then obtain the others. One is positioned in the xy plane. Xy plane means z equal to 0. Okay, x and y yet to be determined. We just leave it there first. Okay, so that is xy plane, center at the origin. So this is xy plane, center origin means that if your field point is along the center, then you know that you can apply symmetrics. Okay, because in the chart it appears to be the sources are symmetric along this center. Okay. The other is parallel to the xy plane. You move the whole thing parallel by a distance d. So every point on the source here, z equal to d. Okay? Along the center means the center point here will be center at 0, 0, d. So both will be centered the same thing. If your field point is along this line, then you can apply symmetry. Anything off this line, you shall do the integration. Okay. Assuming that d is positive, this is just to make it easier to discuss. Your d is on top here, d is positive, y z-axis, and top charge, top dish, positive rho s, bottom dish minus rho s. Minus rho s plus rho s. This is basically the parallel plate capacitor. Okay? You just try to analyze parallel plate capacitor. What is the electric field inside? You are asked to determine electric potential and electric field intensity. Okay, so this is basically, if you are asked to determine electric potential, you have no choice. Suppose they don't mention this, they just say determine electric field intensity. Then you have 2 approaches. You can use direct integration in tutorial 1 or calculate electric potential followed by differentiation. But if a question asks you to determine electric potential first, means that they want you to take this approach. Then you calculate V and then take minus gradients of V. Okay, E is equal to okay. So basically in this case, we wanted to calculate electric potential followed by differentiation, and we have 2 dish, so we do one by one superposition. First obtain what happened at the bottom dish. Okay, so bottom dish, according to this equation here, first, bottom dish located at z equal to 0 now. This is what I mentioned there, source point x, y, 0. First step, calculate delta Q, will be a charge density. In this case, the charge density at the bottom dish is minus rho s. You need to calculate this area here. Is called ds. Okay, the charge density coulomb per meter square. You must multiply by the small area, so that will be a delta Q in this shaded area here. Because this is a cylindrical shape, circle, you need to use cylindrical coordinates so that it's easier to integrate later on. Okay, for example, in the cylindrical, you knew that, I just enlarge this area here. You can easily set up a limit later on to do the integrations, r equals 0 to a, phi equals 0 to 2a. Otherwise, the problem becomes non-linear because in Cartesian, x squared plus y squared equal to less than or equal to a squared. You know the dish, the bottom dish is basically x squared plus y squared less or equal to a squared. Okay, that is a circular dish. There's no good way to do the integration. So when the geometry is cylindrical or circle, use cylindrical coordinate. This call we don't cover spherical, so you don't need to worry about that. Yeah. So just a quick recap. In cylindrical coordinate, everything measured from origin. If you have an area, that will be dr. You cut a small length along r will be dr. Phi is measured from positive x-axis. This way r is always positive. Either you are at this quadrant or this quadrant. R is always measured from origin. Okay? 0 to infinity. Phi is measured from positive x-axis. Go this direction, anti-clockwise. 0 to 2 pi. Okay? And if you have a phi here, this angle, you cut a very small angle here, called it d phi. Okay? This length is r, this small length here will be dr. But we are not interested in d phi. One common mistake, some students write this delta f is d phi dr is not right. Okay? You want to calculate this length here is dr multiplied by this length. Okay, so when you have this r here, and this is d phi, this arc length here is r d phi. Okay? Along a circle, so that when the phi is become 2 pi, you know circumference is 2 pi r. Okay? So it depending on angle, directly proportional. So this arc length here, r d phi. So your area here become r d phi dr. So in this example here, delta cube, the charges confined in this small area here will be minus rho s. R d phi dr is the area occupied by this shaded area. Yeah? Then you know delta Q, Coulomb's law, or in this case we calculate the potential, we know delta Q. Now we need to work out how far away delta Q away from the field point is 0, 0, z along the z axis. Okay, this one unfortunately is not very clear. When you say 0, 0, z, I put it here. How about here? Is it okay? In this question, we need to consider this location or this location, because you need us to compute the electric potential, electric field along z axis 0, 0, z. Should you write it here, here, or here? Anyone? You say here, they say D is positive, huh? D must be on top. Remember that 0, 0, z here doesn't mean that it's off. For illustration, I just do it this one. If you want, you put this one, you put this one. Same. Okay? The math is always correct. Eventually, your solution applies to all axes, all points, either z negative, 0 positive, everything must be considered. So don't assume your z is positive. Okay, this is the only thing I want to know to let you know. If you assume z is positive, sometimes you get a wrong answer. Okay, one, for example, when you have square root of z squared, what is the answer?
Plus minus z.
Plus minus. Square root of 4?
Plus minus 2.
It's plus minus 2 or 2?
2.
2. It's a distant measure from origin. Okay? So this one, this is equal to 2, right? This one? And I'm not joking, you know. Multiple choice, we have no choice. What is the answer here? No plus minus is positive, but you don't know z is above or bottom. So what you need is equal to mod z. Okay, either z is 1 meter above or minus 1 meter, still 1 meter measure from the origin. Is that okay? Or some of them like to write this way, equal to z if z is more than 0, equal to minus z if z is less than 0. Also can. Okay? Basically, when you try to measure distance from the bottom dish, depending on z is positive, this is z equal to 2 meter, so distance will be 2. If z equal to minus 2, equal to minus sign, convey it to 2. Okay? Electric potential, depending on the charge, and the absolute distance. Distance must be positive. Clear? Okay, so there is basically the problems. I just draw it here, just for illustration. Okay? You can put it here, put it here, put it here, see the same thing. So now, we doesn't matter whether it's here, or at the bottom, vector R still field point minus source point. Correct? You draw it anywhere you like, still field point minus source point. This is the math is very powerful. Take into account all these things. Okay, so you just put it in 0, 0, z without saying z positive or negative. Like you understand that z can be positive, can be negative. Minus x, y, 0, you got the vector R. So in this example, we only interested in absolute distance. So it will be x squared plus y squared plus x squared. Doesn't matter z is positive or negative at this moment. Okay? And because you want to do the integration limit in cylindrical coordinate, how to integrate all the charges? You take r equal to 0 to a. You know it's an area, small area here. R equal to 0 is here, r equal to a is here. So you want to integrate this triangle, r equal to 0 to a, and phi must be go from 0 to 2 pi, which means that x squared, y squared must be convert to a cylindrical coordinate before you do the integration. So r squared is equal to x squared plus y squared, simple Pythagoras theorem. Okay? Then you have everything in cylindrical coordinate. Sub in 1, 2, 3 into the electric potential, and you look at this here. If the formula given is a square root, you found that directly you are asked to compute using electric potential because electric potential is R here. Tutorial 1 is 3 over 2 because R cubed. You look at the vector integral, the Coulomb's law. When you direct integrate here, you know that this one will indicate 3 over 2. So the formula given, I'm not asking you to look at this one to then decide the method. But there's a matter of fact. If you are using electric field, direct integral will be 3 over 2. Okay, if you are using electric potential, will be half. Okay, this is a square root here. Okay, but even you are given a formula here, if you wish to do direct integral, you can still proceed. It's still okay to work using both methods. Will produce identical result. Okay? So in this case, we'll substitute 1, 2, 3 and try to simplify it to here. Okay, now 1 over 4 pi epsilon 2 V1 refer to bottom dish, and this is delta Q minus rho S R defined by R.
Sorry.
The distance R has been computed, square root of R squared plus X squared. So for this integral, first you integrate d phi because easier. It's no phi here, 0 to 2 pi means 2 pi. Next, you look at 0 to a. If you compare this integral here now, don't even need to simplify further, just directly compare here. You found that once you change x, the integration formula, the dummy variable x, you change it to r, constant b compared to here will be z squared. Because when you integrate dr, z is a constant. Okay? So directly make this substitution here, this integral will be identical to the integral here. You can write the solution here, changing x to r, b to z squared. So these integrations, how when you evaluate, you have substitute r equal to a, you get square root of a squared plus z squared. Integrate, substitute r equal to 0, you take square root of z squared. So when you try to compute numerical value, don't write square root of z squared equal to z. Remember that this is basically distance measure from the origin. Okay? Square root of z squared is you want to know how far the bottom plate away from the field point. Then depending on whether z is, let's say 0, 0, 2 meters above, z will be positive, it will be equal to z. If you are at the bottom, 0, 0, minus 2, so this will be minus z. Okay? To make it more compact, you can write modulus of z. Always take positive sign. Okay? Or as I mentioned, you can write equal to z if z more than 0, equal to minus z if z less than 0. Any questions? Questions? Okay? Any question? No question. Very simple.
More like don't know what to ask.
Then once you have a bottom dish, in fact from here you know direction of E field already. Because if we look at here, here, E equal to you know that if delta is only functions of z, imply your E field is along z because this is equal to 0, this is equal to 0. Okay? If your electric potential is in x-z plane, your E field will be x-z. Okay? Just looking at the function describing the electric potential, you know in which, roughly in which direction or which plane the E field is confined. Okay, because of this differentiation. So in fact, from this bottom dish, you want to calculate the E field produced by the bottom dish up to the V1. Okay, this del become, when you put the V1 here, is AZ del V1 over there. Of course, you must put a minus sign. Okay, that is the definitions of E field, relationship between E field and the potential. Okay, next one. How about the top dish? Everything the same, except top dish is at z equal to d rather than z equal to 0. So you have distance measure from origin. For bottom dish, you found that you have one term distance measure from z equal to d. Okay? So first delta Q plus rho s ds. ds is the same. Either top or bottom, r divided by r. Distance from here to here, doesn't matter whether this point is here or here, still field point minus source point. Okay? The vector is always right, it's always field point minus source point, that give you the vector direction. Okay? And you found the distance r. You have r squared, z minus d squared. This one is z minus 0 squared. Okay, because bottom d is equal to 0. Okay?
You send me the question again. See.
And integration limit, you see integrate the whole dish, r equal to 0 to a, integrate this triangle, phi equal to 0 to phi, the whole circular dish. And if you carry out the integral, you are going to get these solutions. Basically this one, you just make the appropriate substitution, the constant becomes z minus d squared, you get the solution. Okay? Okay. Now, this just to show you, you don't care. That's why I said that I always just do a very tedious way. Always start from the integration step 1, 2, 3. If you can apply symmetric here, you can directly write down the solution. You found that after you calculate the V1. You look at this diagram here. Electric potential only depending on charges and distance. So the charges is only changed from minus rho s to plus rho s. This minus to plus rho. So you only change the sign, minus rho s change to plus rho s. Next one, how far away? This one, either right here, here, here. Distance measured from origin, z minus 0. Okay? Distance measured from this z equal d, z minus d squared. So in other words, you found that the only difference will be z squared or z minus 0 squared. Okay? Change to z minus d squared.
Given.
So from the solution for V1, you will apply symmetric.
You still don't know.
Minus rho s when you do V2, minus rho s change to plus rho s. And distance measured from origin, z squared here, change to z minus d squared. Okay? The rest is so now we have V total electric potential V1 plus V2. You will combine it. Okay? And the second part is what is the electric field intensity will be minus gradients of V because del X, del Y is 0. The electric potential doesn't depend on X and Y, you only need to differentiate against Z. So that now you have the V1 here. Those who really need to memorize how to do this step because function will change anyway. But you must know how to at least differentiate the square root here. Just quickly when you differentiate against Z here, this is to half. You bring the half here, the power here minus 1, so half minus 1 becomes minus half. Differentiate inside z squared becomes 2z. So now how to differentiate this side here? Square root of z squared. If you are not very sure, you write it outside. Fz equal to mod z. I can write it equal to z if z more than 0, equal to minus z if z is less than 0. So when you differentiate, equal to 1 if z more than 0, minus 1 if z less than 0. Just differentiate because you are not sure whether z is positive or negative, just differentiate it. So what it basically means is potential doesn't depend on the direction. Suppose you have a positive charge on display here. Either your top or bottom, same potential. But electric field point in different direction, that's why you have the minus sign here. Z become 1 and minus 1, basically give a directions of the E field. Okay, so in other words, here, you can write Z over mod Z or mod Z over Z. Magnitude always 1. If Z is positive, is 1, Z is negative, is minus 1. Okay? Suppose in the exam you don't know how to simplify it, then you just write lengthy one. Don't really need to differentiate. Okay? Then the same thing for V2 here. You differentiate the square root. When you differentiate this square root of z minus d squared, when z is more than d is 1. Z is less than d is minus 1. So you have this z minus d over mod of z minus d. Okay? You can imagine that you have the top dish positive charge. When you have more than d is pointing away, more less than d is pointing downwards. Okay, any questions? Yeah, this one easier. If you want, you can take a snapshot. Next question. Okay, a wire loop, question 2. Wire loop means that the charger is along the wire, means rho L dl. Okay? Wire loop has shape of equilateral triangle of side length A. It means that A. I usually hate to do 3D, very difficult view. How do we know it's equilateral triangle? If you take the top views and you look from the Z here, easier, right? So you write it in XY plane, easier. So you rearrange it X, Y.
Shut up.
Equilateral triangle here means side length A, this is A, this is A, this is A. Okay? And 60 degree each. Okay, the equilateral triangle in XY plane.
What the fuck is
Means that Z equal to 0. Okay? The loop is positioned in the. It happened that this guy went. The loop is positioned in the XY plane means that all the wire here, Z equal to 0 because this wire loop is placed in XY plane. X and Y we decide later. So we can write in general X, Y, Z equal to 0. The loop is uniformly charged with charge density rho L. Uniformly charged means that every place the charge is the same. Means that rho L is a constant. Doesn't depending on X and Y. Okay? Because in general, charger can be higher here, lower there, this and that. Uniformly charged means everywhere look the same. Rho L is a constant. Whenever you do an integration, you bring it out from the integral. Okay, so now this is the situation here. And plane at the origin. It means that if you are asked to calculate the field along the origin, anyone along this Z exists here, any point, you get a price. Okay, not necessarily right at this stage. Because in this case, you are asked to calculate the charge density. Suppose at this Z here, suppose you are at the tip here. Center means this distance all same. This is the definition of center. Suppose I am in this position here. I look at this charge. 1, 2, 3. All same charge. Correct enough? And if I have the center, distance also same. I don't need to worry about direction because electric potential no direction. So which means that along, let's say C1, C2, C3, charges the same distance, the same at the center. It means potential must be the same. So which means that you can pick any line to integrate, multiply by 3. Okay? You don't need to worry about which one the charger point in which direction. Scalar at the electric potential only distance and charge. So from this it's very obvious that even though you have 3 lines, you only need to integrate 1 line, and which line to choose. In most cases, choose the line aligned with coordinate axis X, Y, or Z. Okay? So in this case, you look at 1, 2, 3. The easier one is the bottom line here because this line is parallel to the Y axis. Delta Q rho L dl. What is dl? Along Y dy. Along X dx. Okay? So this problem basically can be reduced to just integrate along the horizontal line, multiply by 3. Then you follow the same step. First step, calculate delta Q rho L dl. In this case, dl equals dy. Second step, calculate vector R and do the integration. And you can see that formula given here is a square root. It's electric potential. Okay? Determine electric potential at point 0, 0, Z. Okay, this is a field point. And at the center. So it means that you can apply semantic. It's a given that, given this formula, implying that likely you are asked to compute electric potential rather than direct integral. Because this is the power part. Okay? Okay, so when you integrate here, you need to know what is a coordinate. So basically, you need to know what is how to write the coordinate along the line here. Just to show you that at the center means if this is 60 degree, you divide 30 degree each. All this you meet at the center. Okay? So later we need this. If you not just give your answer in this unknown H. But for the center of the equivalent triangle is very straightforward. You know that from the center to the tip is one portion we call H, to the tip is 2 portions. By simple geometry you can prove that. Okay? So how do you know the H? You look at this triangle here. A cos 30 degree is this AB. A cos 30 degrees AB equal to A cos 30 degree, then you can work out the H. In cases you cannot work out this geometry, usually your answer is this unknown. It's not a big deal in the final exam. Working is more important than science. Okay, but remember that for equilateral triangle, the center to the base is 1 unit, center to the tip is 2 units. Okay, you can determine this height here. This allows us to calculate this, any point along this wire here. You need to calculate few point, source point. Few points given here, 0, 0, z, but you need to know the source point. That's why you need to know what is the height, what is the value of h. Okay, now, just to repeat it, now we have this situation now. We have this equilateral triangle. I redrawn it. The loop is positioned in xy plane, so the source point z is equal to 0. You are asked to calculate at the field point 0, 0, z. You are given the integration formula here. And the charges is along the wire. So delta Q is rho L dy. Okay, now, we always start from this general integral here to calculate electric potential. I'll put a circle here, indicate that you integrate charges in this equilateral triangle. If you want, just write the word bisymmetric, equal to 3 times integrate along C1. Okay, as I mentioned that, charges is the same. Along the center, distance is the same. Potential due to C1, C2, C3 will be the same. Pick any line to integrate, multiply by 3. Usually we pick C1 here because it's easier to integrate, multiply by 3. Okay, so now we simplify to just integrate one straight wire. If this is A, that will be minus A over 2 to A over 2. So we calculate step by step. First, what is delta Q? Focus only along C1, you put the delta Q here. Delta Q is rho L dy. dy because this is along Y. Next one, we need to calculate field point minus source point. Field point is given 0, 0, z. Source point is the coordinate of this delta Q. So, this coordinate here, z equal to 0, you should know, because z is this in the xy plane. We tell you right from the beginning, loop is positioned in the xy plane, so z equal to 0. Now how about x? You found that along this wire here, because it's at the center, if the length here is a, this will be x equal to minus a over 2, y, this is along y. For x, you found that this is x axis, so along y axis, x equal to 0. So every point along y axis, x equal to 0, x equal to 1, 2, 3, and along this wire here, every point x equal to h. Is it okay? So h is a constant. So just now we just shown you that you should be able to work out the h for completeness. But you know that this one is a constant. So we call it h, x equal to h, y. As you move along this source point here, y change from minus a over 2 to a over 2. So we put a y here from minus a over 2 to a over 2. And field point, source point, you do the subtraction, you get the vector r. But for electric potential, we're interested in the distance. So over here will be just square root of h squared plus z squared plus y squared. When we integrate along y, h and z are constant. So basically h squared plus z squared will be the constant b here. Okay? Integration, integrate all the charges, minus a over 2 to a over 2. Okay? So sub in 1, 2, 3 into this, make use of the formula here, you will get the solution. So remember that when you integrate dy, z is a constant, h is a constant, combine this and write it as a b. Okay? The constant b here is basically h squared plus z squared. And eventually you will obtain the solution for electric potential V. And take note that this is in the log function. Don't combine it, because whenever you need to differentiate, you need to simplify log function. You should know how to differentiate log function, but one thing is don't combine. If your solution is, let's say, log, suppose you have log A squared over BC. Before you differentiate, write 2 log A minus log B minus log C. Before you differentiate. Otherwise, you write many lines. It's very, very complicated. Okay? For log functions, simplify all the log function before you differentiate. Okay? This is not necessary to combine log A minus log B equal to log A over B. Okay? As a matter of fact, whenever your source is along wire, current along wire, you end up with natural log. So which means that everyone should know how to differentiate log function. Okay? This is not by accident. You give any source which is along the wire, current flow along wire, you found that in many tutorials you need to differentiate log function. Okay? So for example, this way I just spend a little bit of time looking at here. Okay, the function here, first thing take note that only functions of z, del x, del y is 0. You only need to differentiate along z. So you need to differentiate a log function. Any question? Okay? How do you differentiate this to quick recap? Okay? When you differentiate a log functions of z, write 1 over fz differentiate fz. Okay? You must know this. Differentiation formula never given. Because you are expected, they expect to know how to differentiate a log function. Okay? Example here, when you try to differentiate fz, so if you look at the top here, suppose this is your
Most
fz,
of the learning takes place at home.
log fz. So this is the fz. Because we want to do the log fz here, so this is the fz. I just write it down here. If you copy here, you fz will be here. Huh? I use the same color easier. Okay, this is fz, so that will be fz here. I just copy it down here. So that when you try to differentiate this term, pick out the fz here, that will be your fz. So basically this will be your fz. So you take 1 over fz here, differentiate this term, with respect to z, this constant becomes 0, differentiate square root, half minus 1 minus half here, differentiate z squared to z. Practice a little bit on differentiation. Okay? So that will give you the E field due to the first term. Second term, similarly, you can do it. Okay, that's all. Any question?
He asked me question, I think. Too many.
No question at all. You go big 5 already. Everything very easy, straightforward. It's all step 1, 2, 3, all very simple.
He in zone.
Electric potential, as long as you know which one.
What's this?
Stationary charges, only 2. Direct integral, you know the formula. Formula given.
Keep.
Potential, yeah.
You skip it.
Application.
Yeah. You try out past year, then you know. When you get stuck, then you bring it here to us. Okay? Last one. This one actually comes from part of that. Past year, not very clear. I also feel that I don't know what it's about. What major change, if any, is expected in the value of E if it is evaluated at a point other than Z exists? Okay, I look at the solution, basically ask you symmetric. As long as Z exists, you know there's a symmetric, you can simplify it. Okay, in fact, you found that when you are along the z axis 0, 0, z, when you calculate the vector r, as you can see that your vector r only functions of z, potential only functions of z. Means that E field only along z direction, no x and y. While you are along the center line, you can apply symmetry and you know the result is only along plus or minus x, depending on the charge is positive or negative. But if we are in any point other than if x and y is non-zero, no symmetry, your vector r will be in general x, y. Okay, this one forgot about vector instead of vector on top. For completeness, this one must be a vector. Okay, and the distance r also same. Okay, your result of r will be x squared, y squared, z squared, all involve x, y, z, which means your E field can in general have three components, x, y, and z, rather than just along z. Okay? Who haven't signed attendance? Hey, you took this one now. Where is attendance? Just now I passed you out one.